Okay, welcome everyone. So far our discussion dealing with bases has been mostly focusing on R3. Okay, so a vector space that consists of column vectors. But we have discussed more abstract vector spaces. So let's consider how we can find bases for some of these more abstract vector spaces. So for example, we've determined that the set of all 2 by 2 matrices, that's what mat 2 by 2 stands for, is a vector space when we equip it with the usual operation of matrix addition and scalar multiplication. So 2 by 2 matrices form a vector space. And we want to find a basis for this vector space. And so for any 2 by 2 matrix, right, we can write it as the top row being A and then B, the bottom row being some number C and then D. And that means we can take any 2 by 2 matrix and write it as a linear combination of these four matrices. I can write it as A times the 2 by 2 matrix that has entry in first column, first row 1, and all of the rest zeros. Plus B times the matrix which has top row 0, 1, and bottom row is zeros. Plus C times the 2 by 2 matrix whose top row is zeros and bottom row is 1, 0. And then we have finally plus D times a fourth matrix which has zeros in every position except for the position in the second row, second column. So therefore, we can see here, I can generate any 2 by 2 matrix by taking a linear combination of these four vectors, right, which are now each vector is a 2 by 2 matrix, but we consider these vectors in our vector space. And moreover, any one of these vectors cannot be written as a linear combination of any of the others. So those are our two conditions that we need for a basis. So therefore, we do have a basis B for this vector space of 2 by 2 matrices, which is namely these four 2 by 2 matrices that consist of entries that are all zeros with exception of one entry, which is 1. And so we just pick a 2 by 2 matrix, which has a 1 in one position and zeros everywhere else. And we make sure that we have a 1 in each of these four different positions. So we can see here a basis for 2 by 2 matrices consists of four vectors. This is not the only basis that we can construct, but this is probably the most natural basis that we would first imagine picking for 2 by 2 matrices. Let's next consider a polynomial vector space. P4 is denoting all polynomials of degree at most 4. So we are going to include cubics, quadratics, linear functions, constants, as well as degree 4 polynomials. And we're going to use the usual operations of how we add polynomials by grouping like terms and how we multiply a polynomial by a scalar. And we'll take a similar approach as we did with matrices. So if we have any arbitrary polynomial, degree 4 polynomial, then it can be written as some constant a4 times t to the fourth power plus some coefficient a3 t cubed plus a2 times t squared plus a1 times t plus a0, where each of these coefficients, a4, a3, a2, a1, and a0, these are all scalars. And so now you can see that if I pick any one of these individual terms, right, we really have a linear combination right here of 5 different vectors. And we can name them down below. So now we can pick a vector space that consists of the vector here is the polynomial 1, t squared, t cubed, and t fourth. And so this polynomial is actually just a linear combination of these 5 vectors in our vector space P4. So this vector space of all degree 4 or less polynomials has a basis which consists in this case of 5 different vectors, 1, t squared, t cubed, and t to the fourth.